I'm a couple minutes late. Sorry about that. But let's get quickly to our acoustic waves. Does anybody want to comment on our last lecture, or do you have some questions that before I go on that you would like me to address? So remember, the whiteboard is still like we left it a couple of days ago, and we did a little bit of math, a little bit of physics, and a little bit of math to show that in a fluid, really doesn't need to be a gas, although I said a gas at the beginning, but it can be anything, basically any medium that doesn't support shearing, any medium that doesn't support shearing you would be able basically to do this same procedure. So it works for air, it works for water. The pressure behaves like this, okay? And you see the quantity over there that replaces C, that plays the role of propagation velocity in the equation that we obtained, is something that you can define in any medium that has a density that has, and where you can think of an initial pressure P0. Okay, so at a condition of equilibrium without any sound propagating around, you can measure the unperturbed pressure P0 that you see over here, and you can measure the density of air, and then you can implement this equation. So let's not forget, but let's stop for a moment thinking about how we derived this equation, and let's focus on what this equation means. Okay, so it means that I could, give you a mathematical proof of that as well, but we don't have an infinite amount of time, so maybe we can skip that. But the first thing, that I would like you to realize in view of what we've done so far in this course, what I would like you to think about, what I would like you to see is that this equation is very similar to the equation we obtained for the string. Okay, C squared now, of course, instead of tension, we have a pressure, but it's basically the same equation. It's what we call the wave equation, and we've solved this equation in a simple case, in the one-dimensional case, to find that it would admit, it would admit, first of all, traveling wave solution, traveling waves, or progressive waves, whatever you want to call them, waves, you know, what at the very beginning of this course we called waves. And then also this norm, if the medium is bounded, like in the case of the guitar string, you would also, we have been able to prove that traveling waves that propagate in opposite directions can combine to form a normal mode. What is called, depending on where you look, it will be called normal mode, stationary waves, a standing wave. I wouldn't call it a wave, because at the very beginning of this course, we define as a wave something that actually propagates. So this is rather the sum of two waves with particular characteristics. So in 3 dimensions, you find the same thing. But I'm not going to start deriving solutions analytically. The thing is that in practice, really, the solution, see, in the case of the string, it's easy, right? There aren't so many things that you can do with a string. You can fix, you can stop its endpoints, and you have the guitar string, and it vibrates, and so on and so forth. With a fluid or a gas, you can have a number of different situations. Think, for example, of water in the ocean. It's got to obey this equation, because all the derivation I did, if you go through it, it logically applies perfectly well to water in the sea, in the ocean. But then we also have to think in terms of boundary conditions. So if basically you assume that the ocean is infinite and you apply no boundary conditions, you get what we tend to call sound waves or acoustic waves. And this could be, so the typical example, I mean, the other thing is that then you have at least to specify some initial conditions. So the typical example is to specify what we call a delta, an impulse, an explosion. Basically, if the source, well, let's not call it source, let's specify an initial displacement U, well, P, an initial pressure actually. Let's speak directly of pressure. So let's say that at a time that I call time equals 0, I perturb the pressure in this way. At Dirac delta, look it up if you haven't seen it before. It's a strange entity, mathematical entity with a lot of properties, but the main thing for our purposes right now is that the delta is a function that's 0 everywhere and infinite at one point. Okay, So at only one location, I have a very large pressure. In the real world, it will never be infinite, but this approximates the real world, right? So I have no displacement, no pressure anywhere other than the, well, I should really specify it like that, the way we derived our equation. So there is an initial pressure, equilibrium pressure P0, which is just related to the weight of the atmosphere, of the water. And then there's a very large perturbation to that at time t equals 0. And then the perturbation is gone. It's like an explosion, okay? So sudden change in pressure, and then the whatever process caused this explosion is finished. You know, maybe you explode some dynamite. It takes a second, and then the dynamite's gone, and the system just continues to evolve with no further external perturbation. You just have the effect of this initial displacement. Okay, so that's what we call the grease problem. Yeah, maybe we'll discuss it a bit more in a bit more detail later. But for now, let me just explain what that is. The Green was a physicist, 19th century physicist, who realized the practical utility of knowing how a system reacts to a very simple excitation like this impulse. So he realized, and if I have time, I'll tell you later how and why that turns out to be important. But he realized is that if you know how a system responds to a very simple excitation like an impulse, like a delta, then you can make a lot of inferences about how it's going to respond to more complex excitations. So this is useful because, especially if you, like back in the day, they didn't have computers to model the response of a system to complex excitations. It might be easy to solve a very simple problem by hand, like we did so far in this course. You know, find some analytical solution, and then Green found ways to use that analytical solution to model in a relatively simple way some more complex situations. So solving the Green problems if you solve the Green problem, what you obtain is the Green function, the Green's function, which is essentially the response of a medium to an impulsive excitation, a Dirac delta, and what we call also an impulse. The Green's function is also, sometimes, in some occasions, is also called impulsive response. Of the system. Okay, and in the case of water or gas without any boundary conditions, let me insist on this important point. So if you don't require any boundary conditions to be specified and you just have this initial condition, the Green's function looks like this. I'm just going to write it down. in 3 dimensions, it reads excuse me. Okay, so don't worry too much about this 4 pi. I guess the reason this pi is there is related to the fact that what you see there is, and I don't know how clearly you see that, but it's inherently a spherical sort of thing. In the sense, why? Because everything in here, if you see right away that it's a wave, right? Because in its argument, t and x appear in this form, but it's not quite a wave the way we have defined them so far, because it's also we also have something new. This is divided by this distance here. Okay, so x minus x0 absolute value is the distance of the observation point x from the source x0. Okay, so this gives me the solution at a given observation point x, and the solution depends on its distance from the source. Okay. Forget for a second about this x minus x0. Let's look at the numerator first. What does this tell me? It tells me this is again the Dirac delta, and this tells me that this guy has to be 0. It's a definition I just gave of the Dirac delta, right? It's 0 everywhere except when the argument is 0, except when t equals x minus x0 over c. And when is it, and when, what does it mean that t equals to this guy? Well, that's exactly the moment when this impulse arrives at this point x minus x0, because the time that has passed since the explosion which took place at t equals 0 is exactly the distance divided by the velocity of propagation. Okay, when time equals distance from the source divided by the velocity of propagation, then this guy is not 0. At all other times in this place, in this position x, this guy is 0. Okay? So I understand that I went very fast through several very important concepts. So let me review briefly what I've done. I just defined what we call the Green's problem, okay, for an unbounded medium. Unbounded, it means that unlike what we did with the stringler, we fix the endpoints. Here, I don't fix anything. I'm just imagining to be in a world which is just an infinite mass of water or air, some fluid without any boundaries, without any end. This approach is okay. For example, if you work, if you want to study how wave propagates in a area, for example, at some depth under the surface of the ocean, and you don't care so much about what happens in the distance. So you're only interested in a small part of a very large mass of something. Okay, so if the boundaries exist but are very far from your experiment, then this approach is okay. So we forget about the boundary conditions because the boundaries are very far from us anyway. Okay, so that simplifies, of course, the math. But we do apply some initial conditions, otherwise it's not very interesting, right? So the initial condition is that at the beginning of my experiment, there's no perturbation to pressure. Nothing is propagating. I just have the initial pressure due to weight plus an impulse, and this impulse is localized at one location that I call x0. Okay, and it's represented by a Dirac delta, which is a function that's zero everywhere except at the point where its argument becomes zero. Okay, notice that there's no time here. This is the initial condition for time equals zero. Okay, so this forcing described here, it only exists at time equals zero, and then it's gone. Okay, it's just like an explosion. Boom, and then the explosion is finished, but we face its consequences. Okay, so this is called the grease problem. Studying the response of a medium to an impulsive delta type excitation, localized infinitely small in space, but infinitely large in amplitude source. Okay, spatial extent of the source is essentially zero. It's just 1 point, but its amplitude is infinite. Okay, it's an abstract approximation. Well, yeah, it's abstract, but it functions as an approximation of what happens when you have a very large explosion localized in a small point. Okay, so the solution of the grease problem is called the grease function. And I'm not doing the math. I could do the maths, but I'd rather not do them. And I left it as an exercise for you to see if you can verify this. If you want to do it, it's not an easy exercise, but you can find plenty of demonstrations on the internet, on the other hand, if you're really curious. But I'm just telling you that the solution of this grease problem is this function here, okay? So I ask you for today to believe me, and another things I'm not explaining you yet is why it is so useful to solve the grease problem. It's sort of intuitive though. If you know how, it's easy, to find out how a medium responds to a very simple stimulation, very simple excitation, just a delta, just an attack, just a simple impulse, like clapping my hands. And then once you've measured that or you've calculated that, you can use it to figure out how the medium responds to a more complex excitation. Imagine, if you were an acoustician, you would want to know if in a lecture hall there's a lot of echo. So what do? You go to the lecture hall and you clap your hand. And if there's a lot of echo, you will hear it. You've solved the grease problem. Well, you solved experimentally the grease problem. And now you know that if you go to the lecture room and speak, it will be complicated to understand what you're saying because there's a lot of reverberations, right? If there's no reverberation, it's good. Okay, so that's sort of the idea of the Green's problem, right? You don't want, if you want to know if whether there is an echo, you're not going to say any long sentence, right? You just want to clap your hands, and if there is an echo, you'll hear it immediately. If you just speak, maybe you won't hear it very clearly. It will be hidden by the rest of your sentence, right? So that's a Green's function. And now that I'm trying to give you some elements so that you can start understanding what's the story about the Green's function, what it's all about. Now I want you to reflect with me a little bit about what this formula, what this result is telling us. And let's take it a bit slower. I was a bit too enthusiastic about it and said too many things at the same time. So let's look first at the numerator here. It's again, you know, it's this Dirac here that re-emerges in the solution here. But now you have also time in the argument, not only space. And what this is telling you is when this impulse is going to hit a certain observer. It's going to arrive at a specified observation point. The observation point that we are considering is x here, okay? The Green's function, it gives you the solution, the pressure that is going to be observed. This is pressure, of course, okay? We are solving for pressure there. I call it G because it's just habit, right? The solution of the Green's function is always G, but I could also have written it, and maybe I should have written it as P. Okay, so I apologize for that. Okay, so the solution of this equation with these initial conditions is the Green's function. So this satisfies those initial conditions. If I replace 0 here, I'm back to that situation. Okay, it's exactly the same thing, and because this is infinite anyways, and then it is also the solution to this differential equation as time evolves. So let's look at what happens at time when time evolves. At a given observation point x, I wait. At time equals 0, of course, I don't know anything. I don't know yet about the explosion. The time passes. Nothing happens. Nothing happens. When the time is exactly equal to the distance of the observation point from the source, distance between the observation point x and the source x0, divided by c, which we know from the previous lecture, from here, that has the meaning of a velocity of propagation. In the case of the string, it had the meaning of a velocity of propagation anyway. We see that very clearly. So, well, if distance divided, if time is equal to distance divided by velocity, that's exactly when the impulse, puff, it hits me. Okay, it hits the observation point at x. And then, after the impulse has passed, nothing. Okay, so that's what this delta t minus distance divided by velocity means. It also means another thing, that if you now imagine to take a snapshot, to take a photograph of pressure, of the pressure field, if one could photograph pressure, right? At a given time, so you fix time and you take a picture, this describes a sphere, okay? The locus of all points that are touched, that are reached by this wave at time t, at a fixed time, is a sphere. Okay, it's the locus of all points that lie at the same distance from the source x0. If you're just, if the observation point at time t is just a bit farther away, it hasn't been touched by the wave yet. If it's just a bit closer from the source, it's already been touched and now it's back to normal. So it's got to be at exactly, if you fix time, everything that's moving, everything that is experiences a perturbation in pressure has to be at exactly this distance, x minus x0 from the source. Okay, or to be even clearer, what I mean to say is that if time is fixed, so let's say time equals 10 seconds, well, then delta will be non-zero if and only if x minus x0 equals c times 10 seconds, okay? So if exactly 10 seconds have passed since the explosion occurred, and the velocity of propagation is 300 meters per second, in 10 seconds, the sound from the explosion will be heard 300 meters per second times 10 seconds, 3 kilometers. Okay? Remember, you know, it's an old story. No, it doesn't matter. This is. I think this is clear. I don't have. I'd rather not bombard you with too many examples. There's one last thing that I want you to focus on. And it's this term. This is new. This term at the denominator of this equation. Again, you have the distance. And what does that mean? It means that the farther away you are from the source, the smaller the amplitude of the displacement, in this case of the pressure perturbation will be. So the sound, the pressure in your ears, the fluctuation of pressure in your ears will be smaller. The sound is quieter, is less loud. Okay, if you are farther away. Notice that these, and we've seen that before in my introductory lecture. I threw a lot of general idea about waves at you. So now we meet it again. This is not dissipation of energy. It's not an elastic dissipation of energy. It's not like the resistance of air causes the sound to basically die away. In the real world, that also happens, but in our derivation, we haven't introduced that level of complexity. Okay, we've been treating these fluids as something completely elastic. So what we have here is what we call geometrical spreading. Okay, and remember, this is something that you observe in seismology as well. spreading, because think about it. The wave, what we call the wavefront, okay, the locus of all points that are reached at the same time by this sound, by this click, this explosion, is a sphere, okay? So if you inject through this explosion a certain amount of energy in the system, energy is conserved, right? So 10 seconds later, since we neglect an elastic dissipation, you have the same amount of energy in the system in the form of kinetic energy, you know, and kinetic energy, I'm not doing the math, but kinetic energy is associated to the pressure, you know, the pressure it's there because there's a displacement nearby. So there's a compression or an expansion of the material of the medium, and so the pressure changes. So the kinetic energy, which is halves mass times velocity of displacement square, velocity of this deformation square, has to be conserved. If the displacement is spread out over a larger volume, if a larger amount of material points, of parcels of air or water are set into motion, the same energy basically has to be distributed over a wider area, and therefore locally, if you want energy to be conserved, the displacement and therefore the velocity and therefore the pressure has to be smaller. Okay, and that's accounted for by this term here. So this is a bit different than the waves we've seen so far. This is called a spherical wave. Okay, so obviously all this discussion, it works in 3 dimensions. If we were working in 2 dimensions, it would be a circular waves and it would have slightly different properties, but we're not gonna get into that in this course. In seismology, we systematically work in 3 dimensions, and we are interested in waves that propagate in 3 dimensions. Okay, so keywords so far that I want you to think about. Green's problem and Green's function. Geometrical spreading and spherical wave. In the real world, you're always faced with spherical waves because, well, what I said, it's not exactly true. In the real world, you're faced with very complex sources. Think of an earthquake. An earthquake is not a small explosion, a localized explosion. An earthquake is shear, a fracture that takes place over a possibly very large area. You know, when you have large earthquakes like magnitude 8 or 9 in Japan or in Chile, you might have faults that break over horizontal lengths of hundreds of kilometers, right? So that you can imagine that if you again, if you imagine to take a picture of the wavefront as it propagates, especially in the vicinity of the fault, it's going to look very complicated. It's not really going to be very spherical. What I'm trying to say is that in the real world, in any case, waves come from a source or a set of sources, or an a point source or a combination of points that occupy some extension in space. So if you look, what I'm trying to say is that if you look at textbooks and you will do a seismology course and you will be exposed to seismology textbooks, there's a tendency to do all the math for the case of plane waves. And what's a plane wave? Well, a plane wave is a wave that, just like our unbounded medium, it also extends indefinitely over space. Okay, so if instead of writing this, basically, if I remove this chunk here, then you get a plane wave. Well, I mean, I have to remove this and that. Okay, if there's no source anymore, and this is just yeah. So let's. A plane wave, for example, would be something like this. This is an impulsive plane wave. And see here, this guy is not a vector anymore. It's just a distance along one direction. Which, for simplicity, I took it to coincide with the x-axis, but that was not necessarily, that was not necessary. It's just a way to simplify the math. So a plane wave, again, you have an impulse, but instead of propagating with a spherical wave from a point, it's just propagate as a planar wavefront across all space, okay? So this guy does not go to zero to the left or to the right. It's just an infinite plane perpendicular to the x direction. That if this is the x direction pointing from me to my camera and to you, if this is the x direction, the wavefront propagates like this. Okay. So in textbooks, there's a tendency to show plane wave solutions because those are mathematically very easy. Also very easy to do all the proofs, right? Because we immediately got rid of all the annoying stuff that was there. And also this is a scalar thing. In a sense, it's a one-dimensional thing. There's only one, you need only one spatial coordinate to describe this thing. But the problem is that is not, it quickly becomes useless when you do some real science, because the real world is not infinite. So plane waves don't really exist in the real world. Plane waves are useful as an approximation if you're very far from the source, okay? If you're very far from the source, say there's an earthquake in Japan, and I look at the wavefront across Europe, it's a spherical wave, but we are so far that we are seeing only a little chunk of this sphere, right? A little portion of this sphere. So to us, the curvature is very large, and it looks like it looks planar, and it's okay. We can describe it as a plane wave. But if you're near the source, so if you're doing exploration seismology and you set up some explosive, and you are in the immediate vicinity of the source, because that's how exploration seismology works, then you're dealing necessarily with spherical waves. Okay, and you have to take into account all the complexities of the Green's function. Questions, comments? Good, good. So I'm giving you some time to think about what we just did. So remember that if you want to remember some keywords for today's lecture, we define the Green's problem. I told you, and you believed me, that the solution to the Green's problem for an acoustic medium is a spherical wave which experiences geometrical spreading. And we also learned what a Dirac delta is, more or less, if you haven't met it before. Dirac is the name of the physicist who, I think in the 1950s or something like that, he came out with the idea of introducing a symbol, of actually giving a formal definition to this concept of infinite, but infinitely large, but infinitely localized impulse. And I'm skipping all the math, right, of why that is a solution to that guy with those initial conditions, because there's no time, but you might have occasions to do that in the future. I can send you a formal proof if you want to read it. You just have to ask. And also we've learned to compare. We learned the difference between spherical and plane wave. Okay. And all these just in reference to acoustic waves. There's one last thing that I want to tell you, and I would like you to think about that a bit more when you have time. So I'm talking about waves in water, right? I'm talking about waves in air, sound, waves in water. I'm making it sound like it's all the same thing, and this spherical wave solution, it describes mathematically everything. It's a bit more complicated. And one thing I would like you to be aware of, even if, again, I'm not going to have time and probably even the skills to do all the math, but when you actually sit on the beach, maybe in Trieste, all you have to do is look outside your window and you actually see waves in the water. Those have nothing to do, well, they are not described by the functions that I just shown you. The waves that you see on the surface of the water are surface waves, and they are not described by the math, the physics that we've done so far, because we did not apply any boundary conditions. Those waves that you see on the surface of the water exist because there's a surface there, okay? Because you know, that surface, it kind of works like the fixed endpoints of the string, and it generates some effects that are not taken into account by this equation alone, okay? So when we talk about ocean waves, like, and the most spectacular example is a tsunami wave, okay? When a lot of water is set into motion at the same time, you have a tsunami wave, but it's just, a tsunami wave is just a very large ocean wave, sea wave. Those are waves, but those exist. Well, they result from the presence of a free surface. Free meaning that on the opposite side of the water, there's no resistance to this displacement because there's only air. And also from gravity, maybe that's even more important. Okay, we also neglected gravity in this derivation, but the force that essentially works as it partly played the role of just hydrostatic pressure or tension in the string, is the gravity that so essentially pulls the water back. If I start a wave, the weight itself of the water is the resisting factor that pulls the water back and basically start the propagation of this wave. So in seismology, we speak of body wave and surface wave. You know, you will see that maybe with me, maybe later with Karim, Audia, maybe with both. When you do the math, okay, we will start doing it today. You introduce the equation of displacement. You solve it without applying any boundary condition. You get P waves and S waves. You apply a boundary condition. You say, okay, now I solve the solution for a medium that includes a free surface, no shearing from the atmosphere to the water. So that's a boundary condition, and then you get Rayleigh and Love waves. And when you study waves in the ocean, it's exactly the same thing. Before you apply the boundary condition, you only get acoustic waves, you know, sound that propagates in the form of spherical waves inside the water. The moment you apply the boundary condition on top of that, you also get surface waves, which in the case of water, they're not Love and Rayleigh waves because there's no shearing. So there's no shearing in water. So the physics is a bit different. You only obtain these gravity-driven ocean waves. Okay, so if you are curious to study tsunamis and all that, the starting point is to explore, investigate how surface waves are generated by the requirement of a boundary condition in water. And I do not confuse surface wave in water with acoustic waves in water. Okay, they're really two different beasts. The next step I want to do, if there are no questions on your part, the next step would be to start thinking about elastic media. Okay, you are learning geophysics, so water is interesting, air is interesting to a certain extent. Ultimately, you also probably wish to have some knowledge of how we understand propagation of what we call elastic waves. So this equation basically results in acoustic waves, pressure waves, but elastic waves is what we observe in elastic media. And maybe elastic is not the right word, because acoustic waves, in a sense, they can be called elastic too. So probably I should really say seismic waves. In acoustic waves are essentially, they entail a perturbation in pressure. So it's either compression or expansion. Seismic waves, they involve compression, expansion, but also shearing. So shearing is when you imagine, you always, the way to think about these things is to imagine that you can study some arbitrary surface with any orientation anywhere in the medium where these waves are propagating, and you imagine that you're able to measure all the surface force, all the forces per unit surface that are acting on that surface. Pressure is very easy to think about it. Like, it means that either side of that surface is pushing towards the other, maybe because of weight, maybe because there's a speaker playing some sounds, and you have an alternance of pushing and pulling, because the speaker is moving like this. You're creating a compression or an expansion, compression and expansion. Okay, so we have these pressure waves, and no matter how you orient your surface, air, like water, is unable to sustain any shearing. So all you will observe is just an expansion and a compression. But in a solid, actually, there's also a resistance to shearing, which means that if one side of the material, one side, sorry, of the surface that I have taken through my medium moves tangentially to that surface, the other side resists that. Okay, in air, if I could imagine some particles of air to move tangentially to a given surface, the particle on the other side, they could care less. Okay, they don't resist that. They don't know. There's no. There are no forces that between gas particles that parcels of gas that would resist shearing. But in a solid, the structure of a solid is such that there is a resistance also to shearing. Okay, so you can imagine, it's a bit abstract, but you can imagine a source that generates only shearing in a solid without any change in pressure. Then you will observe only waves that are waves that reproduce, propagate this shearing motion. without any compression or expansion. Okay, so I anticipate that this, depending on how you excite the medium, depending on whether you inject a pressure change, a compression or an expansion, or shearing, a fracture, you can excite two types of waves that that are called P waves or compressional waves, or S waves, which means shear waves. Just as a curiosity, the names, the letters P and S, they come from the fact, and we will discover why, but they come from the fact that P waves are systematically faster than S waves. So in Latin, they are called primae first. They, for a given source and a given receiver position, the P waves are the first to be observed. And the S waves are the second. And then you have the Rayleigh and log waves, but we will talk about that later if we have time. Okay, so now basically I now what I'm going to do next is essentially the same thing I've done for the acoustic medium, except that now I have to add one level of complexity, because the way this medium responds, the way elastic, the way a solid medium responds to excitation is not just in terms of compression and expansion. So let's think of some portion of this medium. And let's think of all, let's do a force balance, okay, for an element of a solid medium. You have essentially two types of forces that we should be careful to take into account. And basically, there are forces that can be applied, forces that act on the whole volume of this material. And the typical example is weight, okay, gravity. Gravitational attraction is a force at distance that doesn't require contact, okay? If this mass is in the gravitational field of something, and if you are in the Earth, you're always in the gravitational field of the rest of the planet. The whole element of matter will be attracted towards the center of mass of this gravitational field by the laws of gravitation. So that's one example. There could be other forces that act on this whole mass. For example, there could be a source inside this mass that somehow, for example, by setting off some explosive, we manage to somehow, through some complex processes, to apply some other forces that interest a whole volume within this element, okay? So I'm just going to use the letter F to refer to those to all those forces, and I'm going to underline it to remind myself that that is a vector. That is a vector. Then we have all the forces that are acting on the surfaces, and that they are associated with contact. Okay, so basically the idea, and this is a very subtle concept, the idea is that the particles, okay, even if we don't know in detail, because all this theory was developed because before people even understood well what an atom and a molecule are. So, but people anticipated, they realized that the particles, whatever they are, that form a medium, that form an element, a certain amount of mass, they interact with one another. There are some molecular, whatever you call them, forces that basically consist in a mutual attraction between particles. A medium tends to stick together, okay, to some extent. So the main property of this type of forces, even without getting too much in the details, but is that they quickly disappear if we consider relatively large intermolecular distances. So they only, in the first approximation, a given particle, a given elementary particle of matter will be affected only by this attraction from the particles that are in its immediate vicinity. And it will not be affected by the next shell, the next layer of matter at a further distance. So for our problem here, the consequences of this idea, of this fact, is that there are some surface forces. Okay, so this is a body force that acts on the whole volume. And then there are some surface forces that only concern the particles that are near the vicinity, near the boundaries of my bodies, of my element of matter. If you consider any other surface within this element, there will be surface forces too. But the thing is that the force on one side of the surface, Newton's principle, are compensated by the forces on the other side. So long as you're within this element of matter, they have no net effect and they don't enter our force balance. Okay, but what enters our force balance are the net forces that the rest of the world, the rest of the medium, the rest of the earth applies to this small chunk of matter. And those are the surface forces. Basically, the only forces that we care about that eventually remain in our equation are those that the material, the particles in the immediate vicinity of the boundary of the outer surface of this mass element apply on those that are immediately on the inside. Okay, and these are called surface forces. Okay, and the sum of body plus surface forces has to equal the net acceleration of my chunk of material. So now this is not just a material point. I'm not writing the force balance just for a material point, but for a chunk, a box, an element of matter that has a volume and an outer surface, small, but not, we don't neglect it. So, because we want to distinguish force and body and surface forces. So let's integrate over the whole element.
Sir,
the body force, like I said, it acts on a volume. Okay, these are typically, this could be weight, right?
sir, please.
So this has to be integrated over the whole volume, but this guy
Sir.
has to be integrated only on the outer surface, because I insist on this point.
Please, sir.
So this is an integral over the whole volume, and this is an integral over the outer boundary of this volume that I call del V. I insist on that point. Surface forces, they cancel one another within the medium, but they don't cancel one another only at the surface of the medium. Okay, because here you have the net effect of particles outside that are not part of my element of matter acting on those that are inside. Okay, and this has to coincide with the total acceleration. So I basically have to average mass times acceleration, of course. So here I have density, and I integrate over the whole volume. And in so doing, I'm basically averaging the acceleration of all particles forming this box to get the acceleration of the center of mass of the box.
Sir.
Okay, any questions about this?
Yeah. Can you hear me, sir?
Yeah, sorry. Actually, my volume was turned down really low. So if someone asked a question before,
Sir. Can you hear me?
Yeah, now I can. Go ahead.
Sir, I didn't understand the difference between the body forces and the surface forces. If you can explain it,
sure.
Please.
Sure. So imagine an infinite medium and take a surface. Let's draw a surface. I'm just gonna draw it like this. Okay, so okay, imagine that the surface is like that. I'm just doing a section through it. Okay, so you have an infinite medium and you have a surface like this across this medium. Now, if one side of, on the one side of this surface, you have some kind of perturbation, particles are moved around. If you are in a fluid and if the motion is only is parallel to this surface, there's no resistance on the other side. This is basically what defines a fluid. Like if particles move parallel to a surface, the particles that are on the other side, they are not affected by this at all. Shearing is allowed with zero resistance within a fluid. But if on the other hand, this motion results in a pressure perpendicular with a perpendicular component to the surface that is non-zero, then these particles are also pushed around. Now, why, if you are in a solid, actually, also if you have a motion that's parallel to the surface, the particles on the other side are affected and they will try to resist this motion. These are facts that we can basically observe with some experiments. Now, why is that the case? What is happening in practice? What's happening is that a solid, unlike a fluid, a solid is an organization of particles of matter, or molecules that want to keep their their configuration. They are in a equilibrium configuration that tends to stay the same. There are some interparticle forces that tend to keep the particles always at the same distance from one another. Think of crystals, you know. So if you push it, if you push one side of a solid body, the other side will resist this pressure, right? This happens also with fluids for slightly different reasons. If you shear it, again, the other side will resist this pressure. So if you pull it also, or if you shear on the other side, you will have an equal and opposite resistance. Okay, so these are all things that we can, by logic, speculate, given the behaviors that we observe. Now, how do we describe that mathematically? Well, if I shear, okay, the particles, if I move the particles on one side of this surface along a direction, say parallel to the surface, the particles on the other side, they tend to keep them where they are through this intermolecular. The particles right here, they don't care. They don't know what's going on because they're too far, because this intermolecular force, they only act at very short distances. So the only place at a given moment, of course, then we have waves and disturbance propagate, but that's a different story. So at a fixed moment in time, if you have a perturbation here, it will only be the particles on the immediate other side of the surface that will resist that disturbance. Okay? So the force that results from this phenomenon is called a surface force. Again, it is a consequence of the structure that we think that by now we know that matter has. It's not related to weight or anything like that. It's just the forces that keep matter together, that keep a crystalline structure together, for example. And I repeat, you will only be able to measure it near the surface because at a farther distance, you're too far. Okay, so does that make sense?
Yeah.
Good. And then a body wave, on the other hand, can be weight, gravity. Weight, you will feel it even if you're very far from the center of mass of the body that's attracting you. Weight is a force at distance. It doesn't require proximity, doesn't require contact.
Yeah.
So, good. It's a very delicate point to understand. So, yeah, I have a few more minutes. Basically, what I want, yeah, yes. So I want to say that, well, first of all, for those of you who have done a little bit of math, we will do it next time, but think about this situation here. This equation, what we want to do, this is not only for those who did some math, but for everybody. Then I will introduce a mathematical concept that some of you might know and some probably won't, but in any case, we'll cover that next week. But Now, for everybody, this by itself is a difficult equation to deal with. We have three integrals, two volume integral and one surface integral. So, you know, our ultimate goal in all these exercises is to reduce everything to a situation like that, where you have a differential equation with only one unknown function, which holds at any point of your medium. So if you solve that equation, you have the solution at any point of a medium, no matter where the observation point is. That means that you have solved the problem. That means that you have a tool to predict how a system will evolve following a given excitation. So here we are very far at this point from being in that nice situation, and you can imagine that we want to do a couple of things. First of all, we would like to write everything in terms of displacement. Okay, these surface forces I already anticipated. They are related to the relative displacement on the two sides of the surface that bounds my element of mass. So this presumably is something that can be written in terms of displacement, and that could be our goal. Hopefully we'll be able to do that. Okay. And the same for the body force, which of course gravity will change depending on your distance from the center of gravity or whatever. But I anticipate that in this course we are going to neglect the effect of gravity, so eventually we don't worry too much about this thing. The other problem, so we want to write everything in terms of displacement, okay. The other problem is that here I have a volume integral, here I have an integral along the border, the boundary of that same volume. If I had two volume integral or two surface integral, it would be good, because I could, everything would boil down to the integral of the sum of difference of these two integrands, of these two arguments of the integral. And then, since my element of mass, remember, I just took a random brick of any size, provided that it's small, anywhere in my medium, it's completely arbitrary, right? So if I can show that the integral over this arbitrary volume of something is zero, it's the same thing of saying that the function that's integrated is zero itself. Because I can take this guy as small as I want, so ultimately I can just integrate around a point. Ultimately, what's inside has to be zero, right? So I want to do two things. I want to reduce either the second integral to a surface integral or the first integral to a volume integral. And I want to write everything in terms of displacement. So the first thing we're going to worry about, well, the way we are going to reduce, I don't know if it's the first thing, but the way we are going to reduce the surface integral to a volume integral, and this is the mathematical concept that for now I'm just going to throw at you, is by the divergence theorem. And some people call it the Gauss theorem. Although Gauss did so many things in his life that it's kind of confusing to call things Gauss, because there are so many things that are called Gaussian and Gauss this and Gauss that. So probably better to think of it as a divergence theorem. That's a mathematical result that essentially allows us to write a surface integral that extends of a vector extending over a finite surface that encloses a finite volume. It can always be written as the volume integral of the divergence of something. So I'm just anticipating for those who want to look ahead and prepare beforehand that next week I'm going to tell you about the divergence theorem next Monday. Before I leave you, I also want to give you one last piece of information to anticipate what we're going to do next. It's useful to write, well, I mean, it's useful. Like, how many parameters do we need to describe as this to provide, or to have all the information that describes the surface forces that act on this chunk of element? Remember what we did for the gas. We decided, since we are dealing with very small arbitrary volume, it's completely okay to take a volume that has the shape of a cube. And the sides will be oriented also to make our life simpler, like the Cartesian axis, x, y, z. And then, if I do that, the surface forces on this side, for example, here, on this face of the cube, will be described. So I call it T. Let me call it T Z, because Z is the direction that's perpendicular to this surface. So it identifies the orientation of this face. So Tz will have three components that I call Tz X, Tz Y, and Tz Z. And the same for Tx, okay, which will have three components like this. So if you consider the three possible orientations here, you have you have another of these guys. T Y X, T Y Y, and T Y Z. So if you take these three vectors together, you have what we call a matrix or a tensor, and this contains both the pressures, okay, which this Txx, for example, is the force on the x surface here in the x direction, which is like this, and so on and so forth. So this contains both pressures and pressure and shearing forces. And basically, I haven't. This is what I written on the blackboard is not quite the stress tensor, but I will do this more rigorously next week. But you see, if you've done some continuum mechanics, and if you've done some geophysics courses, you probably have done a bit of continuum mechanics. You might have met the stress tensor. So this is what is going to come out of this reasoning there. But for today, I'm not going to give you the details. I'm just telling you this is where we are going. So from the concept of surface force, we are going to derive the concept of stress tensor. The point that I would like you to absorb from today's lecture is that it's not surprising that we end up with a 3x3 matrix, because to describe the surface forces that act on this cube, you need 3 × 3 components. Why not 6? Because what I'm gonna do next, just like we did for pressure, right? If here I have Ty, here I'm going to have Ty plus delta Ty, because everything is small, right? So I don't need, I don't want to have another independent value of the stress tensor on this surface here, because this is infinitely small. So this will just be a small perturbation to the value that I have there. Okay, so eventually everything will boil down to the derivatives of these guys across our across the space, actually across the distance, over the distances. Okay, it sounds like enough material to think about. I'll take your questions, but don't ask me to derive the stress tensor, because or the divergence theorem, because that we're going to do that on Monday. But if there's something you would like me to clarify about what we've done before in this lecture, please go ahead. It's good enough. Ready for the weekend. See you on Monday. Yeah.
Yeah. Ciao. Goodbye, sir.
All right.
Thank you,
you very much.
Thank you, sir.
Bye. Have a good weekend. See you on Monday.
Thank you.